use properties to write alternate forms of logarithmic expressions. So given something like log base 3 of 9z to the 4th, we could first apply the product rule and say log base 3 of 9 plus log base 3 of z to the 4th. We know that 9 is the same thing as 3 squared, leaving everything else the same. They match, so they cancel. So one way of writing this is like this form, but I can also go one step further and bring that 4 out front, the power, and write it like that. What if I do log base 6 of square root of n over 3m? Well, first, that's log base 6 of n, that's an m, over 3m to the 1/2 power. Pull that number out front, and I get 1/2 log base 6 of n over 3m. Applying the quotient rule, I get log base 6 of n minus log base 6 of 3m. And there's really not, there's a couple more things we could do. We could split this one up too and go one step further and say log base 6 of n minus log base 6 of 3 plus log base 6 of m. The only thing you have to remember is to put this second piece in parentheses, because both have to end up in the denominator, so this negative needs to distribute to both pieces. Say I was given log base 2 of x plus 3 log base 2 of y minus log base 2 of z. Well, this can come up to the power. So I have log base 2 of x plus log base 2 of y cubed plus log base 2 of z. Minus log base 2 of z. A plus means with the same base, I can combine in one log as a times. A minus with the same base means I can combine in one log with a divide. So I can expand and I can simplify them back together using the properties of logs. Log base 5 of x plus 10 plus log base 5 of x minus 10 minus 3/5 log base 5 of x. And we're going to assume x is bigger than 0. Same base with a plus means I can stick them inside of the log being multiplied. And in the same step, I'm going to raise the 3/5 as the new power. Foiling this out, I get log 5 of x squared minus 100. Because they're conjugates, you only have to times the first two and the last two. And because this is a minus, this becomes on the bottom of the divide. These two things are not being multiplied, and so this cannot be rewritten. There's nothing you can do to this. Rewritten. Mathematicians should possibly learn how to spell as well, right? So what if we're given that log base 2 of 7 is equal to 2.8074, and log base 2 of 10 is equal to 3.3219. And we want to evaluate log 2 of 70. Well, we know this is 7 times 10, so we can rewrite it to be log base 2 of 7 plus log base 2 of 10 by the product rule. We know this is 2.8074, and we know this is 3.3219, so adding them together, we get 6.1293. If I have log base 2 of 0.7 is what I want to figure out, well, that's the same thing as 7 divided by 10. Using the quotient rule, log base 2 of 7 minus log base 2 of 10. And I know log base 2 of 7 is 2.8074. Log base 2 of 10 is 3.3219. So I get negative 0.5145 as my evaluation. Given log base 2 of 49, well, this is 7 times 7. Using the product rule, I can split it up into 2 times. So I have 2 log 2 of 7, which is 2 times 2.8074, which is 5.6148. Let's do 2 more examples. In these examples, we are going to look at situations where we want to decide whether the statement is true or false. So given log base 2 of 16 plus log base 2 of 16, is that equal to log base 2 of 32? 3, 2, 1, giving you time to think. No, false. Reason being, if we have 2 of these things being times together, we can times them inside, not add them by the product rule, which would make it a number much bigger than 32. What if I was given log 2 of 4 times log 3 of 9? Is that log 6 of 36? Yes, no, yes, no. False. This one can become log 2 of 2 squared times log 3 of 3 squared, which we know, since the insides match, I'm left with a 2. Insides match, I'm left with the 2. The final answer would be 4. Versus this one, log 6 of 6 squared is just 2. They don't evaluate to the same number. 4 does not equal 2. That's why it's false.